Welcome to our Year 10 video on measuring speed. This is our third video of our motion and forces section. Here are our learning intentions for this unit, and as always we'll work through each of these as we go. Our first learning intention: to describe how ticker timers, light gates, which are also called photo gates, and motion sensors measure speed. So these are all pieces of equipment that hopefully we will get to see in the lab once we're back in there after COVID. First one, our ticker timer. What you can see here, we have this, which is our timer, and through the timer we have some paper. It's like a paper, a bit like a tape measure, but it's a plain piece of paper, and it runs through the middle of the timer. In the timer there's a little piece of graphite that bobs up and down and hits spots onto the paper. So what happens is the object that you're measuring the speed of has the ticker tape stuck to the back. The object moves, the paper pulls through the timer, and the little dots hit onto the paper. The faster it goes, the bigger the gap between the dots, and that's the idea of our ticker timer. Next up, we're looking at this idea of the light gate or photo gate. So here we've got some equipment set up, and this is the photo gate. So what it does is it measures the speed of the object as it passes through. Now sometimes you might have two light gates set up, so that measures the time that an object went through the first light gate and then the time it went through the second light gate. You know the distance between them, you can work out its speed. So they work, you can do different things with light gates in physics. Measuring speed is one of them, or motion. And also we've got our motion sensors. So this is our Pascal sensor that we use in our labs at school. And we saw already how we can measure motion using our motion sensor, because we've done that practice before COVID. Our learning intention 2, to be able to set up a ticker timer or equivalent to monitor the motion of an object. So I know you can set up motion sensors. I've seen you do that. How about ticker timers? Well, let's watch this video.
When you come to ticker timer up to the power supply, make sure that you connect the timer to the AC part of the power supply. It goes. Unscrew or screw up this particular part. Then you've got some control over how fast it's going up and down. To put the paper through, and ensure that the paper goes.
It's got to go under the carbon paper.
The carbon paper.
Otherwise it won't get dots on it.
Tape goes through and it's banging onto the tape.
So the metal is going to put dots onto the paper. I'm going to skip through a bit. Now what he's going to be doing now is he's just tying an elastic to the front of the little trolley, because he's going to pull the trolley with that elastic. Now he's going to connect the ticker tape to the back of the trolley.
The tape is easier to handle. Stick it on the trolley. Make sure it's free to move. Then we're all ready to go. Turn on. Then you've done your journey and you end up with a nice tape with a series of dots on it.
There's all the dots. So that's how you use a ticker timer, and hopefully we'll get to do one in class soon. All right, learning intention number 3, to be able to interpret and describe the motion represented on distance time graphs. All right, distance time graphs. So we're going to have distance against time. Some words we might want to use: increase, decrease, constant speed. We might be using accelerating, decelerating. All right, just remember, later on we're going to have to start looking at gradient to find speed. So your formulas from one of the previous videos are going to become important, be important, because we might need to know some of these formulas to do some calculations. So always refer back to these. Okay. Also, whilst we're on this area, we're going to start linking in this new term, velocity. Now, if you look at that formula, velocity equals distance divided by time, doesn't it remind you of something else? Speed equals distance divided by time. Interesting. So velocity is the same as speed, but it's got direction. So I'm traveling at 50 kilometers an hour, or I'm traveling at 50 kilometers per hour south. The second one is velocity because I've got direction involved. Okay, talking about graphs, talking about distance time graphs. If we're talking a steady increase, okay, a steady increase, that's what we're seeing here. Now, car A is covering less distance in the same time as car B and C. Now, this graph is horrible because that 0 should be at the origin of the graph, but for some reason my graphing skills on Excel, on PowerPoint were not good, and you're going to allow me to have this error. Now, car A travelled at a steady speed but covered less distance in the same time as car C. Okay, they all travelled the same time, 1.5 hours, but car C travelled 120 kilometres, whereas car A only travelled about 30 kilometres. Okay, so they travelled at steady speed, but obviously car C travelled at a faster speed because it went a further distance. All right, in this graph we can see that the time it was taking the car to travel was changing. Okay, and this car's accelerating as it goes. The others are travelling at that steady speed. This car is increasing its speed as it goes. Decreasing. Okay, so these are decreasing at, so we say a decrease. Think about what's happening. They all started at a certain distance away. So this car started 20 kilometres away, and these two both end at 10 kilometres away, whereas this car gets right back to the initial start position. Okay, but that's steady. Then we might be seeing that deceleration here. Okay. All right, stationary. So time is going by. We've got time on the bottom, 0.5 to 1.5. But the distance isn't changing for any of our cars. So car A is 10 kilometres away at half an hour, and it hasn't moved the whole time, so it's stuck there. It's either stuck in traffic or parked. Car B is at 20 kilometres away, and it hasn't changed over time. And car C is at 40 kilometres away, and it hasn't changed over time. Alrighty, so one of the things you quite often have to do around this area is tell the story of the graph. Okay, so this graph, we're looking in meters. This is me out for a walk. So I leave home. Home is 0. I walk 40 meters. took me 20 seconds, so I could work out my speed there if I wanted. Then I stop and have a chat. Now I go from C to D, and my pace increases as I go. Okay, then at D, I stop for another chat, and then once I'm at point E after my chat, I walk all the way home at a nice steady speed. Okay, so it's telling the story of the graph. And I'm walking home to where I started. Now here, this is when things get really interesting, because we're still talking positions. So this is our starting position. So see this maybe like, imagine it's a boat and this is a map. So our boat went out to sea that far. Okay, this is the coast along here. So we went out to sea over here, then we stopped in position. We're having a bit of a fish. Oh, we've heard there's good fish right over here, but we've gone past our start point. And then we've gone up to there. So these graphs are showing us, yeah, this movement, but this direction is where velocity is going to come. This is a great website, which I recommend you have a look at. I can't open it at the moment. We'll look at it in class. Good website. Okay, learning intention number 4. You need to be able to plot distance time graphs from a supplied set of data. Now remember in your exam, some of you were losing marks because you didn't have a title. You plotted your axis wrong. Distance is the y-axis. Distance is the vertical axis and time is the horizontal axis. Okay. Making sure you get your units right and things like that. All right, calculate the gradient at any point of distance time graphs to determine the instantaneous speed of an object. Whew, some words there. All right, so maths. How do we find our gradient? Okay, it's our slope, isn't it? It's that rise over run. Okay, so remembering, we count the units of our rise, we count the units of the run, and then to find the actual speed, you then divide 4 by 3, and if we're looking at meters per second, it would be in meters per second. So here's an example. Here's one I drew myself for you. All right, so we're doing rise over run. So we've got 10, we've got 15. So 15 is our rise, 10 is our run. 15 divided by 10 is 1.5 meters per second for that speed at that point. I would lose marks on this graph because look, my title is column 1. Okay, you can also find the speed, remembering, and this would be velocity if your line was a negative. All right, so the negative does suggest that we've got that negative slope. Again, you would do your rise over run, remembering that on a negative line you get the negative units involved. Okay, you need to be able to physically reproduce the motion represented by simple distance time graphs whilst monitored using a motion sensor. I believe we did that in class. Okay, so you've already done that. You've made some distance time graphs. Wouldn't it be good if we can do it again now we have this understanding? Take it easy, guys. That's the end of this video, and remember to subscribe to my YouTube channel. See you in the next video.